Okay, so welcome everybody. I'm going to talk a little bit about query troubleshooting. Now, all of the examples and the details I give you are going to be about Postgres, but both MySQL and SQLite also have explain. They work along the same principles, although of course the details and actual code terms are a little bit different. So, what's explain? Um, you know, why should you care even? Well, so if you're running an application in production, you have eventually run up against the application being unresponsive because of being out of resources or taking far too long to fulfill requests. And when you're not fulfilling requests, you start out with your sort of timeout troubleshooting, right? So you figure out which of your requests are being slow. You trace those requests, and sometimes it's your code, or something else that's causing the request to be slow. But sometimes you find out what you are waiting on is a database call, right? And you figure out which database call you are waiting on. And then what? So the next step there is you need to figure out what the query is that Prisma is generating for that database call, right? Because you've already traced your code. And so now it's time to trace the database's code. And the database's code starts with uh, an SQL query. You can do that inside Prisma by going ahead and logging queries through Prisma, possibly through that individual call, which would be recommended rather than generating a ton of output. Um, Alternately, if you are doing a performance audit of your entire application, you can set up Postgres. I know you can do this in MySQL. I'm not sure whether or not you can do this in SQLite, but you can set up your database to log all queries, or to log all slow queries, which is actually the combination that I'm showing here for Postgres in the Postgres settings, so that you can actually see what's running and do a performance audit of the whole application. Either way, you end up with a query. So now you have a query, you know which query or set of queries is slow. So what's next? Well, what's next is explain. So what the explain command does is it shows you what the query planner um, chose to do, how it chose to fulfill your request, gives you stats on how the query actually was executed, implies some reasons why the query was slow, um, does tell you which individual step in the query took the most time. What it's not going to do is, if a particular step in the query is really slow, tell you exactly why that is broken. There'll be hints, particularly if you use some external tooling to help you gain insight from this. Um, it also, one of the most important things is there are other reasons for a database call to be slow other than query execution, such as round trip time between the database server and the application pods or servers, and other things. So you always need to potentially anticipate those. Um, so, but explain is our next step in tracing why our database requests are slow. So the rest of this talk, I'm going to actually go into exactly some of the basics on how to read and explain so you can gain insight into why your individual database requests are slow. So, but in order to explain what explain does, I have to actually give you some background on what the query planner is and how it works. Because what you are reading and explain is the query planner's own output. Um, so how a query planner works, and again, this is true across SQL databases that I know, is it breaks the query down into bits of work called nodes, as in retrieve this bunch of rows from this table, then correlate the bunch of rows with some from another table. So it breaks it down into nodes. It figures out every possible way to execute each node, and the approximate amount of work that they'll take, chains that together into what's called a query plan, and then figure out what the cheapest query plan is. The Postgres query planner was originally written in Lisp. I think it still shows, even though it's no longer in Lisp, in how it's organized. So now in Postgres, the individual nodes all have the same sort of format, right? Which is for each node, you have a set of rows going into the node from the database, a set of parameters that were supplied by your query, either directly or by implication, and then you will have a row set coming out of it. Um, so for example, if you're on a sort node, which does what it says on the tin, what you're going to have coming in here is the rows from retrieving data from a table, the sort columns that you have given the query, and the output will be sorted rows. So to look at that in code here, so we're now doing tracing via the explain command. Um, this is what a sort node would look like, right? And so this is saying, hey, we've got 808 rows that we are sorting. Here is the sort key that we're sorting on this. Here is the, and then some detail about how the sort was implemented, that Postgres decided to do a quick sort. It needed 43 kilobytes of memory, etc. So this is the individual node for just a sort step in a larger query. Now, what I'm showing you here is the text mode that comes directly on the PSQL console when you are doing explain. This is what I'm going to show you through the rest of the presentation. I actually do not recommend that you use this. Instead, I recommend that you use one or more of the helper tools that give you a more graphical explain. The reason why I'm using the text mode in this presentation is simply that the helper tools do not make for good slides, largely because I can't enlarge the text, whereas I can do that in text mode. One of the helper tools that I've used for a long time, a guy named Hubert in Poland maintains this website called explain.depsys.com. And you get your text mode explain plan out of Postgres, you paste it in there, and it actually breaks it down into steps, and plus gives you some hints as to what the query planner is doing, including what it is doing wrong. There is a second web tool called PEV that does this now in a more modern format where you can actually see the query as a tree structure. And see it that way and drill down. And if we actually were to click down through some of these, you could actually see more details about what it was doing in that step. These graphical formats are actually going to help you a lot. You'll notice that it's giving you hints as to which individual nodes are executing badly. These are going to help you a lot. I strongly recommend that you use them, even though you're going to see text mode in the rest of this presentation, just because I need it for slides. So one of the things that we talk about here a lot is cost. The important thing to know is you're going to see these cost numbers. These cost numbers are arbitrary. They're only meaningful in comparison to each other. A lot of people try to translate them into, say, milliseconds of execution, which generally does not work out. They're not meant to be that. People play with some of Postgres's parameters to try to get them to line up to milliseconds of execution, but that's always only approximate. Costs are only comparable to other costs. They're not comparable to any real world figure. So again, so here's an example of a very simple query. So we are querying one table, looking up a library patron based on their library card number. And it's going to go straight for an index scan, which makes sense. And this is giving us, hey, we're doing the index scan. It has this low cost. And this is the index condition that it is looking in the index for here. And again, there's that cost, but that cost is only comparable to itself. And it's a very low number. I've been telling you, slow queries tend to have costs in the tens of thousands or the millions. Single digit costs generally relate to queries that Postgres at least thinks are going to be extremely fast. So one of the other differentiations, and this is a specific Postgres thing, I don't think it applies to MySQL or SQLite, which is explain versus explain analyze. So explain says, query planner, tell me how you plan to execute this query and what the parameters are, right? Explain analyze says, tell me how you plan to execute this query, execute the query, and then come back and tell me how you did. Important note here, if you are analyzing a query that changes data, like an update or insert or delete query, it will actually update, insert, or delete. So if you are just testing the query for speed, you might want to do it in a transaction so that you can roll it back afterwards. You can see here the difference is we're doing now an explain analyze, right, of that same query. And so we've got the plan here of doing the index scan and the index condition. And then we actually have some data about the node, right? It took 0.1 milliseconds for the planner to plan the node, and it took 0.07 milliseconds to actually execute that and retrieve the patron record, which happened to be in memory because it's a small database. So there we're getting our actual execution information. You can get a lot more execution information with analyze and a bunch of parameters. Now, this means that most of the time that you're doing this, you want to use explain analyze, because that will actually tell you a lot more about where the query went wrong and why it was slow. The only reason why you wouldn't use analyze is either the query takes literally forever, um, you're just checking whether or not the new index you created is going to be used, um, or if you have a partition table, you're checking whether or not its Postgres is correctly making use of the partitioning to only access one partition instead of the entire giant data warehousing table. So most of the time, you're going to want to use explain analyze in Postgres. There's a bunch of other explain options, buffers to show memory usage, costs and timing to show a bunch more detail. You can do different formats. You can get a lot of additional detail. You can play around with these. Buffers, for example, shows you memory usage from Postgres' perspective, which might be different from the OS's perspective. You can do it in different formats to make it more readable or more machine digestible. If you're using the PEV graphical tool, for example, it wants you to do JSON format as its input. Verbose gives you a lot more information about what's being queried. Actually, verbose is really useful for detecting one common problem, which is if you have a very wide table, like a table with 45 columns, and you actually only need one of those columns, if the query is being generated badly by the ORM, you might actually be retrieving all 45 columns when you don't need all 45. And that causes the query to require a lot more memory than it would otherwise. So let's talk about how you actually read this output, right? Because I've shown you a bunch of examples. Let me explain what they actually mean here. So the first thing to understand about Postgres Explain is that it's what we call an inverted tree. As in, the stuff that's executed first is at the bottom and the stuff that's executed last is at the top. And it's also indented that way. So for example, this is the first step in this query. It does a bitmap index scan on the lone partition table. Next, it actually simultaneously does two different steps. We're joining two tables, and so Postgres will actually take advantage of IO weights in order to scan two other tables simultaneously. And then on the third thing, it will actually do the join of those two tables. And so that's the sort of ordering of it. And even if you use the graphical tools still have stuff in inverted trees. And so you need to understand that, because otherwise you might look at the top and assume the thing at the top is what's being executed first, whereas it's what's being executed last. So let's look at one line of explain here and explain what you're seeing here. And again, in the graphical tools, you're going to have the same details, just in a different format. So the first thing it'll tell you is what operation it's doing, an index scan. So we're looking up something in an index. And the second thing it'll tell you is the approximate cost with details, right? So what's the planning execution cost expected for this? How many rows do I expect to retrieve? And how wide in bytes are those rows? So one of the things that you'll notice is these costs cascade upwards and they overlap. So in some cases, the second step of execution doesn't begin until the first step is completed. So like right here, we see we're ending on a cost of 151 and we're starting on a cost of 151. So this step doesn't start until this step is completed. But this step apparently can start while this step is still in process. And so it tells you a lot about sort of parallel execution that way. Um, and same thing with sort of a final step. And you can actually kind of understand this, right? Where if Postgres is waiting for rows from disk and it's getting them a block at a time, it can start sorting them while it's waiting. Now, actual will then show you what the actual execution time was. And now this is in milliseconds. It is not relative to everything else. It is actually absolute milliseconds. Um, down to the microsecond, which is our resolution in this. If you are doing this on a Windows server, the resolution is lower than that. Windows Server doesn't give us microsecond resolution. I don't remember exactly what it is. The and how many rows it actually retrieved. When this actual is radically different from the expected, that's one of your signs of a problem. One of the other things here to look for is loops. That loop figure is a multiplier. So 7 rows with 1,200 loops actually means roughly 10,000 rows total. It'll give you some conditions, which are generally things that you pass through your own query or are there because of joins with another table. Um, and those are sort of our parts. And then you can have a bunch of other stuff like buffer usage, et cetera, depending on the options that you're doing. Now, one of the things we're going to have is a lot of operations, which are also known as node types. These are different things that the query executor can do. I'm not going to go through all of these in detail during this presentation because we have to finish up. Look at the slides, which are public, and I'll post in the comments as well. There's a bunch of kind of scans are, let's get data from an index or a table. And Postgres has a bunch of different kinds of scans. MySQL and SQLite have fewer different kinds of operations they can do, but same general principles. So here's an example, a bitmap heap scan, which is a special kind of where you scan the table, construct a bitmap in memory, generally for joining it against another table. Example, joins. Speaking of joins, we have a variety of ways to join two tables together. Postgres picks the different kinds of joins based on what it thinks will execute the fastest. There are a bunch of these. I actually wrote this series for Postgres 11. It's Postgres 13 now. I imagine there's probably another kind of join by now. But there's a bunch of different kinds of joins. Examples of actually a hash join or merge join. The most common ones you're going to see are nest loops and hash joins. They get used more often than anything else. Then there's aggregates, and this is for aggregating data generally as a last step in a query. And Postgres had different ways to execute aggregates in an effort to maximize speed and minimize memory usage. So here's a hash aggregate or a group aggregate. And then there's a bunch of other operations like making data unique, doing a sort, limit for limit offset that can happen in your steps. And then there's a bunch of other miscellaneous operations. And this is actually kind of pretty much just a Postgres thing because Postgres has all of this complex stuff in its query executor. So things like a CTE scan. So I don't know if you've handwritten any queries. Some of those queries may use what's called a with clause, which is a more readable way to do a subquery. And so that will bring the CTE scan node, and there's subquery scans and materialize and append. Materialize is one to look for because it often uses a lot of memory. And again, with a slow query, that's one of those things you're actually looking for. So CTE scan example. So all this comes down to, hey, let's figure out why is my query slow? Well, so I'm going to give you a few examples here. And again, those graphical tools I showed you, and I'll show you again, will give you hints as to which individual steps might have a problem. But I'm going to show you this right here. So this is an example. One of the most common reasons for your query to be slow is that you do not have an appropriate index for the query you are actually running. So like here, for example, we have a query against a table that has 200,000 rows. And we're not using an index. This term in Postgres, sexscan, is another one to look for. Sexscan is Postgres speak for full table scan. And again, not something you want to be doing against a large table. Against a small table, full table scans are great. Against 200,000 rows, not so great. And you can see here, right, is that we're filtering, we're removing it. And so what this says is I probably need a different index than what I have there. Either an index and category, and whatever it is I'm joining against in the rest of the query, in order for this to be some kind of index scan. Another example here that you'll see all the time is bad row estimates, and this is where those graphical tools can really help you. So here you see that Postgres thought that this index scan was going to return 100 rows, where it actually returned 10,000 rows. So that's 2 orders of magnitude off. And why this is a problem, like if this was the last step in your query, it actually probably wouldn't be a problem. But if Postgres is then joining this against another table, it could be a real problem because it'll use the wrong kind of join based on being 2 orders of magnitude off. There's a fair fuzz factor in this. If it's like off by double, you don't really care. But if it's off by an order of magnitude, you do care. And again, those graphical tools will give you hints as to when you've gotten a bad row estimate. Another thing you actually want to look for is time-consuming loops. These can often be invisible because each individual loop does not take very long, but you really want to look for times when Postgres is looping thousands of times, because again, that's a multiplier, right? This is only 0.03 milliseconds, but it's 0.03 milliseconds 10,000 times, which adds up to a significant amount of time. And in a lot of cases, this means messing with indexes to encourage Postgres to use a different kind of join that would not produce that loop effect. Or if you've handwritten a query, taking out a subquery, turning a subquery into a join, other simple things. So basically, now one of the things that you can do in Postgres is you can start a transaction. You can run explain. There's a whole bunch of query parameters that you can change in your terminal, in a PSQL terminal, that will not affect how the server is running for everyone else. And so you can change those, and then you can run explain again. And that's particularly a good thing to do if you're thinking about changing Postgres settings on the server for everyone, like random page cost is a common one that you will see on Stack Overflow that people like to mess with. Well, you can do that in an individual session and see if that's going to change the query plan in a way that you like. I want to say, so now to finish up here, like I said, I do encourage you to use the graphical tools. They will make life easier for you. Here's explain depth again. Here's PEV again. There are some other tools. These are desktop tools, PG Admin, PG Analyze. And if you're willing to use IRC, the folks on the Postgres channel on Freenode get bad queries all the time and will help you troubleshoot them if you are patient. So I don't know how much time we have for any questions. I think I actually ran to the end of my time there, but I'm happy to take questions in chat while the other speakers are presenting. Stop sharing.
Thank you for the insightful talk, Josh. I already have one quick question. We'll see. We have a couple of moments for questions from the audience. So if you have some questions, feel free to ask them in the comments. One of the questions that came up is, I know that you stressed the fact that cost was an arbitrary and a relative measurement. I was wondering, what are the two numbers? What is the sort of the meaning of the two numbers that have the two dots between them?
Very important. Thank you. Sorry, I meant to mention that. The first number is the expected cost of retrieving outputting the first row. So remember, every node outputs a row set, right? So that first number is the expected cost of outputting the first row. And the second number is the expected cost of outputting the last row. So sometimes those two numbers will be identical, particularly if you're only outputting one row. Sometimes they will be different for that reason. And that's actually super important if you are doing a query with a limit, because Postgres will actually give you the cost. Like it might say 1 to 10,000 is the cost, but if you're doing a limit 100 on your results, it won't actually get to the 10,000.
I see. I see. And that will also happen already at the execution. So this is not something that can be determined at query planning time.
Yeah, that'll. Well, I mean, you can look and see that there's a limit node in there, right?
Mm.
But to see what it actually did, yeah, you'll have to try and explain analyze. Should I answer Dimitri's question?
Yeah, that'd be great.
Okay, so Dimitri's asking, in the course of development, what's the best practice in terms of when to do this sort of analysis? Any opportunities for automated checks? Um, so, in general, for most people, most applications, 99% of your queries will be fine. 99% of your database requests will execute within your SLO and will not be an issue. So, given that, most of the time you actually want to wait for a problem. You want to do this as problem troubleshooting analysis, right? As in, you have a slow request in in your application and you've traced it down to a database call, right? So that is sort of the normal way. Now that said, some people have applications that have super tight SLOs or that are expected to scale to millions of users, under which every single millisecond is important. And for those sorts of applications, you might actually want to do a general audit. And if you're going to do that, you probably want to have a database expert on staff or as a consultant to help you with that. And there's a couple of different ways to do a general audit, just to answer your automated portion of the question. One is to turn on the logging options. Like I said, Postgres has a ton of logging options. MySQL has a ton of logging options where you can have it log all queries, which I actually recommend because sometimes what's being slow about a database request is not that the individual query is slow, but that you're doing it 1,000 times. Um, you can log only slow queries. You can log a bunch of details of the queries. You can log memory usage. You can log a whole bunch of other things. So basically, you can output this performance audit log in either Postgres or MySQL, and then run it through a variety of tools that are available to help you analyze that log. PG Analyzer is one for Postgres. There are a couple of others, and therefore see how optimized your application is. And it's particularly when it's actually particularly useful is if you're anticipating growth, right? So if you see that a particular query against your users table is being a little slower than you'd like it, and you know that you're expecting your users table within the next 6 months to be 1,000 times the size it is now, then you probably need to do some index optimization now rather than waiting for it to break down. The second thing you can do in Postgres, and I don't know if there's an equivalent in other databases for this, is there's a tool called auto explain where you can trigger it outputting the explain plan if it meets certain conditions. And you do that in the Postgres settings. At least through Postgres version 11 or 12, though, auto explain had to be set up at restart time for the database, and it produces a lot of output. So it's a little awkward as an audit tool. I don't know whether or not that particular issue has been fixed to allow you to dynamically turn auto explain on and off without requiring a server restart, which is would make it a lot more useful from that perspective. Because the problem with all of this auditing is it really produces enormous amounts of output. Like in a busy database, I've seen full query logging produce, 50 gigabytes an hour of log output. And you obviously don't want to have that on all the time.
Great. We have no more questions coming from the audience. I think one final question that I think would be interesting to finish the talk with would be, generally speaking, besides slow queries that can happen due to execution, lack of index, and one of the many reasons that you mentioned, what are some of the common reasons for slow queries besides the ones that you've mentioned?
Yeah, so right, I would say top 3 reasons for slow queries. Like I said, so I mentioned not having an index, right, which is really top. Right. Second one is Postgres is, and I didn't go into detail in this, but Postgres is stats being bad essentially. So Postgres asynchronously samples the database in order to maintain statistics about what's in the database, how big certain tables are, how the rows in those tables are organized, etc. If those statistics are sufficiently wrong, they are always approximate, but if they're sufficiently wrong, it can cause Postgres to take a really bad query plan. Like, for example, if you just bulk loaded 1,000,000 rows into a table that used to have no rows in it, the queries that you run immediately after that bulk load may have really bad query plans. Um, there's a variety of ways to solve this. You can increase Postgres' sampling rate. um, I recommend if you do a bulk load call analyze on the database, the analyze command on the database immediately after the bulk load in order to minimize your sort of window of having bad stats. And then sometimes the bad stats are just a result of the limitations in Postgres statistical models. If you look at the 1 hour version of this presentation that I do, towards the end, I talk about one of Postgres' classic problems, which is something called abort early plans, which is a stats problem. And that's actually an example of something that you kind of just have to work around by munging the query. Because it's a shortcut that Postgres takes that can speed up your query by like 10,000%. But when Postgres is wrong, it slows it down by 10,000%. Um, the so and then the last one is insufficient resources on the database server.
Right.
If you need to sort 1,000,000 rows and you have no memory available in the database server, Postgres is going to sort those on disk, which is significantly slower than sorting them in memory. If you're seeing a lot of that, and this is where that buffers option comes in with explain, if you're seeing a lot of missed buffers, then one of the things that you can do is take your database instance, increase its physical memory. Postgres also has memory limit settings for individual queries, etc. And that's the second thing you can do is explaining is increasing those memory limits. The most influential one for queries is called workmem. And workmem is just a limit, it's a resource limit on the total amount of memory that a query is allowed to take per operation. And it's to prevent too many concurrent queries from running the server out of memory is the reason why that limit exists. But if you're doing a lot of big data analytics type queries, data mining type queries, it's pretty easy to need more work memory than that, than the default. And the question is a 1 hour talk, this one entitled Explain from 2015? Yeah, I did this in 2015 and again in 2016, I think. And yeah, if you found that, that's the correct one, and it'll talk in more detail about some of these steps.
Thank you so much, Josh. That was very insightful, and I look forward to digging further into the slides and trying this out.
Oh, and I'll post as soon as I figure out how can I actually comment? Interesting.
You can either access that via YouTube or you can drop the link in the private chat and then I'll share it in
Okay.
the comments.
Okay.
Great. So all the best, Josh.